In this section, we will talk about even and odd functions. Let's take a look at an even function first. In an even function, f of negative x equals to f of x. In other words, when you replace the input with negative x, it still equals to the original function f of x. Also, the graph of an even function is symmetrical across the y-axis. Now let's talk about what this means, symmetrical across the y-axis. So your y-axis is the vertical axis, it's this thing. If something is symmetrical across the y-axis, it means that it looks exactly the same on both sides of the y-axis. So for example, if this side of the y-axis looks like this, then the other side of the y-axis will also have the very exact same shape, except reflected over the y-axis. Okay, so this is being symmetrical across the y-axis. Also, a polynomial function will have all even exponents if this is an even function. Okay, here's an example. Let's take f of x equals to x squared. First, we're going to find out what is f of negative x. So the input is negative x, which means the x gets replaced with the negative x. Remember that this x is just a placeholder, and that x gets replaced with the input, which is negative x. If you take negative x and you square that, it gives you x squared, which is the original function. So this tells us that f of negative x equals to f of x. Because f of negative x equals to x squared and f of x also equals to x squared, so f of negative x equals to f of x. If you graph the function f of x equals to x squared, it looks like this, and this is symmetrical across the y-axis. In other words, if you take the y-axis, it looks as it's a mirror image on both sides of it. So therefore, and the exponents are all even. Therefore, f of x equals x squared. This is an even function. Let's take a look at an odd function. For an odd function, f of negative x equals to negative f of x. Okay. Secondly, the graph is symmetrical about the origin. Now let's take a look at what that means. Symmetrical about the origin. So that means if you have a point like 1, 1, being symmetrical across the origin, it means that the same point will be reflected about the origin, so that 1, 1 becomes a negative 1, negative 1. So both of these signs change. Let's take another point. Let's say we have a point like 2, 4. The reflection of this point, so this point is the point 2, 4. The reflection of this point about the origin is going to, so you change both of the signs, make it negative 2, negative 4. Just down there. I know it's kind of getting in the way, but that's what it means to be symmetric about the origin. That any given point, if you change both of the signs of the x and y, that should give you a point on the other side of the origin. And then a polynomial function that's an odd function will have all odd exponents. So example, we have f of x equals to x cubed. First, let's find out what is f of negative x. So let's take the input negative x and replace this x value, which is a placeholder, with negative x. So we have this x gets replaced with negative x, and negative x cubed is, well, negative x cubed, because you have a negative times a negative times a negative, and that gives you a negative x cubed. So what's happening is our original f of x is x cubed, and if you replace the input with negative x, it gives you a negative x cubed. So f of negative x equals to negative f of x, which makes this an odd function. Here's what it looks like graphically. This is symmetric about the origin, which means if you take this, and imagine you're taking this whole thing and you're flipping it about the origin, it's going to look like this. In other words, this point is 1, 1, and we have a corresponding point negative 1, negative 1. This point is 2, 8. We have a corresponding point negative 2, negative 8. So you take any point, change both of the signs, and that point with the changed sign should also be on the graph. That means the graph is symmetric about the origin. and exponents are all odd. So in this case, for it's a polynomial function, we have odd exponents, so that makes this an odd function. Here's an example. Determine if the function is even, odd, or neither. So the first one, if we look at it graphically, it's symmetric about the y-axis. This is your y-axis, and it's same on both sides. So this is a reflection about the y-axis, which makes this an even function. Okay, let's take a look at the second one. For the second one, do we have a reflection about the y-axis, which means that this will be the exact same mirror image on the other side? Not quite. It's not reflected about the y-axis. So therefore, this is definitely not an even function. Now let's check to see if it's an odd function. For it to be an odd function, it's reflected about the origin. So any point here should have a mirror image on the other side, which it doesn't. So it's not odd, which means that this is going to be neither. Okay, lastly, let's take a look at this one. So let's see. So we got to check three things. One, or two things. One, do we have a reflection about the x-axis? If so, that makes it even. Two, we got to check, do we have a reflection about the y-axis? Oh, sorry, about the origin. I'm sorry, there should be reflection about the y-axis. That makes it even. Then we got to check, do we have a reflection about the origin? If so, that makes it an odd function. If it's not either of these, it's going to be neither. So let's see if we have a reflection about the y-axis. And if we did, then the same shape would be reflected, the mirror image of it would be on the other side, which we don't have. So that's not it. Do we have a reflection about the origin, which means take any point and it should be reflected about the origin. So that same point should be on the other side of the origin. Let's take over here. That same point should be other side of the origin. And it is. So this is reflected about the origin. And that makes this an odd function. Okay, so always check, is it symmetric about the y-axis? Then it's even. Is it reflected about the origin? Then it's an odd function. Let's take a look at part A. We got to check if these are even, odd, or neither. So here, this is the y-axis, and we do have a mirror image on both sides of it. The same image is reflected about the y-axis, which means this is going to be an even function. This next one, is it reflected about the y-axis? Is it the mirror image on both sides? No. Is it reflected about the origin, which means for any given point, is the mirror image on the other side of it? No. So that makes this a neither. Okay, let's check the last one. First off, do we have a reflection about the y-axis? So is there a mirror image on the other side? No. Let's check to see if there's a reflection about the origin. So this point, is it reflected about the origin? So the same point, does it happen on the other side of the origin? It does. Let's take another point, like let's take like this one here. Is it reflected about the origin? So take this about the origin, and yeah, it is. So that makes this an odd function. Okay, next one. Determine whether each function is even, odd, or neither. So first one, if we take if we're given a polynomial function, let's look at all the exponents. So we have all even exponents. And we learned here that a polynomial function with all even exponents is going to be an even function. But we can see that on the graph as well. This is the graph of this is reflected about the y-axis, and that makes this an even function. But we can tell even without the graph because the exponents are all even. Okay, let's take a look at the next one. Here, the exponent is even, here the exponent's odd. In a polynomial function, if you have two positive exponents or two negative exponents, if in a polynomial function, I'll repeat that. If in a polynomial function, if you have all even exponents or all odd exponents, that makes this either an even or odd function. But you have one even, one odd, which makes this a neither. And you can see it on the graph too. It kind of looks like it's reflected, but if you look at the distance here, it's not the same on both sides, so it's not a mirror image on both sides of the y-axis. So this one is neither. Here, this actually be a 0.5x cubed. So please correct that in your notes. This should actually be an x cubed. All right, let's take a look at the first condition. Just by looking at it non-graphically. Here we have an exponent of 3. Here, if it's x, exponent of 1. And here we have an exponent of negative 1. Well, all the exponents are odd. 3, 1, and negative 1. Even if it's a negative, it's still an odd number. So 3, 1, negative 1, these are all odd exponents. So just by looking at it, by looking at the actual function, I can tell that it'll be an odd function because all the exponents are odd. I can also tell by looking at the graph, because if I take this point, there's a mirror image of it on the other side of the that's the origin. So take this point, we have a mirror image on the other side of the origin. You can do that with any point. Let's take this point, and we have, if you reflected about the origin, that's going to be this one. So we have a mirror image about the origin, which makes it an odd function. Okay, let's take a look at this one. F of x equals to the absolute value of x. So the graph of it looks like this, which means that this is reflected about the y-axis, and that would make this an even function. Now the absolute value of x, it's not a polynomial function, so if you want to test it algebraically, you can figure out what is f of negative x. So in other words, we're taking the x and we're replacing it with the negative x, so that'll give you absolute value of negative x. But the absolute value of negative x, that's equal to just x. So f of negative x, well, sorry, that equals to the absolute value of x. So f of negative x equals to f of x, so that makes this an even function also. Okay, then we got f of x equals to x squared minus 2. All right, so first, let's check to see, just looking at the equation. So we have x squared. Now, I'm going to give you guys a little hint. If there's no x, that means it's x to the 0 power. Okay, if the variable x isn't there, it's x to the 0 power. And in this case, we're going to say that x to the 0 power, we're going to consider this to be even. Okay, so now let's just look at the exponents of the polynomial function. The exponents are both even. We have 2 and 0. So in this case, we're going to consider x to the 0 to be even. So because we have both even exponents, this is going to be an even function. And we can see that because it is symmetric with respect to the y-axis. There's a mirror image on both sides. Next, let's take f of x equals to x cubed minus 2. So remember, if there's no x, you're going to put an x to the 0 there. If there's no x to the 0 power. So 3 is an odd exponent and 0 is an even exponent. So because we have one odd and one even, this is going to be neither. And we can see that there's no reflection, there's no symmetry about the y-axis, there's no reflection about the origin, and that makes this function neither even nor odd.